Hi, and welcome to my REACTO screencast. So today we're going to look at a problem that we see here at Full Stack, particularly when we're talking about data structures. It's about finding a path in a given graph. The problem is called solving graphs, and it's as follows. Basically, you have to write a function that determines if a path exists between the two vertices of a directed graph. The function takes in three arguments: the graph itself, which is really a tree of nodes, which is why we see it in the tree data structures part of the course. A starting node and a target node, and it will return a Boolean to determine whether or not it's possible, given the graph, to reach those nodes from the start. Yeah. And if we see here, we've got the graph with 4 nodes, and each node has the given path it can access. Let me see, I can just represent it here. So we've got node A, B, C, and D. Okay. And given the structure here, we can go from A to B, and B can go to C and D. So B can do this and this. C can get to D, but D won't really go anywhere. C can do this, but D doesn't really go anywhere. Yeah. And, well, how do we solve this? We basically have to traverse this whole thing, which is the first thing I think about is recursion. But where do we use recursion? Let's see. First, we got to establish that we have certain vertices already accessible, right? From the very start. And we can do that by going to these, just putting them in an array. Where we use that handy object structure and we use a start, which is a string, a node of a string. No data on that node, just the name of it as a key to that one. So great, now we've got that, and we can immediately check the very first possibility of whether that array includes our target. Because if it does, we immediately want to just go ahead and return true. Say if in this one we're looking for B, like right here. We run that, and it returns true. That's awesome. We've got the first case down. But how do we get to check if B can get to A? We'd have to actually go down to the B array. If we just run this right now, we're not really, we'll return undefined, we're not really checking the B array. So, but we want to be able to go through the same path we've already gone. So the next thing to do, in my opinion, would be to start a for loop, and let's go through just a regular old for loop. Let's go through each element there and put that in. Yeah, we go through each one and put that in the beginning. So we're going to basically do a callback. Can we go? And we take the graph again. And this is where we use the element of the for loop, the vertices available at I, and a target. And we're going to make this a circuit, that we want to break out of. That way, even the recursive call will return a Boolean and break out of this too. Yeah. Okay, so let's check that now. Where this time we're going to put in B here. Or actually everything that is in A, which in this case is going to be B. But then it's going to go and, okay, let's go check B, C, and D. And C, it's going to check the D, and D, it's going to be nothing. Let's see how that goes. Great, that actually works pretty well. We know that this works, and this works, and this works. Great. And this works. Awesome. Right now, you might be thinking that we solved this. However, there are some edge cases that we see. For example, here's another graph. Let's pull this up above graph B, graph A. And now we're gonna see some other cases we can use this function for. So the first one is, oh yeah, self-referential. Here A is got a clear path to A, so this should return true. Awesome. C would return to C. Great, yeah, because we did it just like previously. And R, yeah, R should be accessible. I mean, S should be accessible if you start at R. Let's see. Oh, that's a problem. So we don't actually want that to happen. But why is it happening? Basically, it's because A is self-referential at the beginning. And that's leading us to just stay stuck there, basically. If we console log vertices at I, let me see. Let's see. Oh, yeah. Well, in any case, if we keep seeing where the vertices are, you'll see that we stay at A. I don't exactly remember right now where to console log this. It's been a minute since I came up with this solution. But the answer to this is to make an additional check. If we put here a continue, it's going to keep going despite finding it there. And you might be wondering, well, I kind of wanted to break out of the loop and return true. But the thing is, it will in the recursive call anyway. And here we put the recursive call now in an else statement. And bring this up here. Cool. Oh, it's because I wasn't, okay, hang on. I'm gonna basically undo this so that I can show you guys. And this is the one we want to check for. There we go. So yeah, you can see that because A, the node is self-referential, and it has a path to itself, it will stay there, and the recursive call will never stop going unless you exceed maximum call stack. So as I was saying, we want to put this if statement here to check, well, not really to check, but to basically continue. And else. Okay, Now let's see what happens. Very quick callback, not exceeded. It's because it kept going and checked checked C, which checked down to R and checked that one and checked S and got a true anyway. Great. Now let's check the last case. Right on. Also working. Awesome. So this was my solution to this REACTO. Additionally, there are other more optimal solutions that were taught here at Full Stack, particularly this one. It's using something kind of like memoization, where it's keeping track of the places visited using this object. If you start and, well, first base case, return false, and if it's not there. But if the start is in the visited object, then we can return true. So that is already operating on that. And this is actually a super careful base case where if there's nothing connected to the start, say, okay, right now this runs false as expected, but say we didn't have this B here. That's where it would break out up here. Oh, well, that was also false. So that's not a very good demonstration. But let's see. Okay, let's see A to A, or just A to B. Cool. And now here, right. So that's this in action. And this is actually a more optimal solution because of the use of this object. Because we're not actually doing as many calls as in my solution. I just thought my solution was a little bit more straightforward to visualize, especially given the way that we go through this. We just keep checking and go back and keep checking and go back. All right, thanks. That was my REACTO for solving graphs.